So now we're going to discuss when to shift and when to reduce. So we discussed about how a shift reduce parser works, but we have left some open questions, and one of the questions is when to shift and when to reduce. So let's look at this example again. So we have our usual grammar, which is the grammar of expressions, and we have the string int star int plus int. Now the red line separator represents our cursor, and I could either shift this separator to the right or I could reduce at the top of the stack on the left. So we also said that the left substring can be represented as a stack, and so I could either reduce at the top of the stack or I could push to the stack by shifting. Now at this point there was a choice. So this location here, there's a choice. I could either reduce or shift. And if you recall, in the successful derivation, in the successful reduction, we actually shifted. Let's look at what happened. What would happen if we reduced? So we could have reduced int to a t using this production t produces int. So if I do that, then this would be actually a fatal mistake, because once I do that, then I would have to eventually shift to the right. And there is nothing, there's no production in our grammar that starts with either t star or, I could even reduce t to e, and there's no production here that starts with an e star. So if I do a reduction at this point, I have actually no hope of being able to reduce all the way to the start symbol e. And so it was important that I don't reduce and I shift at this step. Okay, so in other words, we want to reduce only if the result can be further reduced to the start symbol. I mean, that's the informal intuition of when we want to reduce, right? So we just saw with an example that some reductions will not eventually lead to the start symbol while others would, and so we want to identify which reductions would lead us to the start symbol and which won't. And we also said that we could always implement a backtracking based strategy, but now we are interested not in a backtracking strategy but a predictive strategy. So we want to predict whether to shift or reduce. So to be able to predict, we're going to develop a series of concepts before we actually present the final algorithm. And one of the concepts is the concept of a handle or a definite, and this is just a definition. So consider a step in a rightmost derivation of the start symbol s, and let's say I'm making multiple steps, so that's represented by the star here, and at some point I end up with this string alpha x omega. Alpha represents a string of symbols which could be terminals and non-terminals. Omega also represents a string of symbols which could be terminals or non-terminals, and capital X represents a single non-terminal. And in the rightmost derivation, this would, let's say, produce alpha beta omega, using the production X produces beta. Alright, so if this is a rightmost derivation and this was indeed a step in the rightmost derivation, then I'm going to call alpha beta, which is the prefix of this entire string alpha beta omega, as a handle of alpha beta omega. Alright, so a handle identifies a reduction step that can further reduce to the start symbol. Notice that in this step I am reducing, or actually in this, because I'm doing a derivation, I'm deriving beta from x. In the reverse direction, I would have reduced beta to x. Now, should I have reduced or should I have not have reduced? Well, that is exactly same as answering whether alpha beta is a handle or alpha beta is not a handle. If alpha beta is a handle, then I should have reduced, because I know that there is a path all the way back to capital S. On the other hand, if alpha beta is not a handle, then I shouldn't have reduced, because then there wouldn't have been a path all the way to capital S. And this is just the definition of a handle, right? Because if there exists a path like this, if there exists a step like this, then we say that alpha beta is a handle. Okay, so let's look at an example to understand more about handles. So first of all, we only want to reduce at handles. We don't want to reduce if it's a non-handle. So if it's a non-handle, then we want to shift. If it's a handle, then we want to reduce, because we have hope to getting all the way up to the start symbol. Okay, so let's look at this grammar that we're quite familiar with, and then let's try to understand whether something is a handle of this grammar or not. So once again, this grammar basically is the grammar of expressions. E produces t plus e or t. T produces int star t or int or parenthesized e. Now, is int a handle of int star int plus int? In other words, should I be able to reduce int to some non-terminal when I see it on the leftmost side? All right. So let's try to derive int star int plus int using e. So because it's an unambiguous grammar, actually there's going to be only a single derivation, but I want the rightmost derivation. So there's going to be only a single rightmost derivation. So I say e produces t plus e, produces t plus t, produces t plus int. Notice that I am deliberately doing only a rightmost derivation. That's a property of the shift reduce parser. So I can't just decide to derive the left t before the right t. That won't be a rightmost derivation. And then I produce int star t plus t. Okay, so now if I look at this, notice that in this step I derived int star t from t. So which basically means that int star t is a handle of int star int plus int, because on the way back I could always reduce int star t to t, and I would still be able to get all the way back to e. But I've already, it's an int star, so I didn't really reduce t to an int, or I didn't derive int from a t, so I shouldn't be able to reduce int to a t. And so in fact from this we can say that while int star t is a handle, I couldn't find any step here that was just deriving int. All right, and so int is not a handle. So the answer here would be no. Okay, so recall what is a handle once again. It represents, so there should be a reduction step such that the prefix of the string was obtained by reducing so alpha x. So if alpha x omega produces alpha beta omega in a rightmost derivation, then alpha beta is called the handle. So in this case, int star t would be called a handle. So in this case, alpha would be just epsilon, and beta would be int star t, and x would be capital T. And nowhere in here did we have a step which actually derived just the single int. And so int is not really a handle, because we don't really have a step here in the derivation, in the rightmost derivation, which derives int on the leftmost prefix of the string. So the answer is no. Okay, let's look at some more examples. So is int star t a handle of int star int plus int? Well, we just saw that int star t is actually a handle. So once again, to see that, e derives t plus e, it derives int star, derives t plus t, derives t plus int, derives int star t plus int. Now this point, this represents omega, this represents x, and alpha is represented by the empty string. This represents beta, okay, and this represents omega. So there is a step, and alpha is still the empty string, right? So alpha is the empty string. Okay, so indeed there is a step that derives t plus int to int star t plus int, and so int star t is a handle of int star int plus int. So the answer is yes. Okay, all right. Now let's look at another example. is int star t plus e a handle of int star int plus int? So let's again try to derive this. So I say S derives, E derives, E is our start symbol, so E derives t plus e, and it's a rightmost derivation, so I'm going to say t plus t. Okay, but here I'm asking whether it's int star t plus e, but I have already had to derive t from e because it's supposed to be rightmost derivation, and so I will never be in a state where I have the string int star t plus e, because the symbol at the right of plus is already a t, and I without a parenthesis I won't be able to get back to an e, and I don't have a parenthesis in int star int plus int. So I won't be able to have a situation where I have int star t plus e ever in this state of the derivation. And that is because I would like to point out that that's purely because it's supposed to be a rightmost derivation. Notice that if it was not a rightmost derivation, then I could have, for example, derived from here int star t plus e. So I could have derived t first into int star t and then later done other things, and in which case this would have looked like it is a handle, because now I can in future steps go all the way to int star int plus int. But this is not acceptable. We are only looking at rightmost derivations, and in a rightmost derivation such a prefix string can never appear, and so this is not a handle. All right, so int star t plus e is not a handle of int star int plus int. So notice that there are two conditions for it to be a handle. Firstly, it should appear as a prefix of the string in some step, and second, that appearance should be formed by an immediate derivation, right? So in the reverse direction, I should be able to reduce it. Okay, so in this case, it just doesn't appear. In the previous case, which was this case of int, it did appear as a prefix of the string, but there was no derivation that was producing only int. The derivation was producing int star t, so that's not. So we won't consider the single prefix int as a handle. In this case, it doesn't even appear, so it's a very easy answer that no, this is not a handle. Okay, finally, one more example. Is epsilon a handle of int star int plus int? Now, indeed, epsilon appears as a prefix, with epsilon represents the empty string, so indeed epsilon appears as the prefix in actually a lot of steps, or all steps of the derivation, the rightmost derivation. However, there is no step that actually derives epsilon from a non-terminal, right? So for example, I just say E goes to t plus E. There's no step here. I mean, I can go all the way to int star int plus int, but there is no step here which is going to derive epsilon on the leftmost side of the string from a non-terminal, because there is actually no production that produces only epsilon in the grammar, and so the answer here is no. Okay, all right. So far we have only said what a handle is, and so we have tried to understand what a handle is, and we are saying that we should only reduce at handles. All right, so we're going to see that more in a bit, but we haven't really talked about how do we efficiently find them. So how do we determine whether something is a handle or not? So for example, we said int is not a handle for int star int plus int, but int star t is a handle. All right. So how do we decide that? Or even int star int is a handle. So how do we decide that? So that's something that we are going to learn in the subsequent modules. But let's look at another important fact that's related to handles. So in a shift-reduce parser, handles appear only at the top of the stack, never inside. So assuming that whenever there was a possibility of reduction, I'm reducing by identifying whether it's a handle or not. And I'm only shifting if there was no possibility, if there was no kind of handle reduction that could have led me to the start symbol, then I will always be reducing only at the top of the stack, never inside, right? So handles will be appearing only at the top of the stack and never inside. So why is that? Well, first of all, it's true for the empty stack, so for the empty stack, there is no inside. So if there's if the cursor is to the leftmost of the input string, then there is no inside. So I could either reduce the epsilon character to something which is the top of the stack anyway, or I could not do anything and shift. So any reduction that's happening in the empty stack is on the top of the stack because the stack is empty. So there's no reduction that can anyway happen in the middle of the stack. But in general, consider the rightmost non-terminal on the stack. All right, and so the claim here is that the next handle can only be to the right of this rightmost non-terminal, and this is coming from the property of the rightmost derivation. All right, so let's look at it in a little bit more detail. So let's say I have this string at any point in my stack, alpha looking bottom to top, alpha capital X beta y a b c, where x and y represent non-terminals. Now I'm saying that the next reduction, so what is the rightmost non-terminal in the stack right now? And then there is this omega, and omega is basically just a string of terminals because you haven't even seen it. All right. So what is the next handle that will appear, or what's the next reduction that will appear? Well, the next reduction can only appear to the right of the rightmost non-terminal. So it can only be to the right of y. It cannot be to the left of y. So I can't say that, oh, the next reduction is actually x beta goes to z or something like that, or beta goes to z. That won't happen, because if the next reduction is to the left of y, then this sequence of reductions would not trace a rightmost derivation, right? So the next reduction has to be to the right of y. Why? Because only then would the reverse of this would be a rightmost derivation. Because if the next reduction is to the left of y, then that basically means, in the reverse direction, I'm deriving something on the left and then something on the right. So let's say, the next reduction is reducing beta. Then in the reverse direction, I have first produced beta, and then I'm going to produce from y, and that won't be a rightmost derivation. Okay. So for it to be a rightmost derivation, it must be true that the next reduction is to the right of y, never to the left of y. And that's just a property of the rightmost derivation. Okay. So with that, to summarize, handles are never to the left of the rightmost non-terminal. Handles are never to the left of the rightmost non-terminal and are thus always on the top of the stack. So if I have some kind of a stack, then the handle is always on the top of the stack, because I can't ever say that, okay, handle is somewhere in the middle, because if I have to reduce, I will be reducing on the top of the stack, or I will be moving right, because the next handle will only be to the right, never to the left. And hence a shift reduce parser can only either shift or reduce at the top of the stack. And this is something that we have been assuming so far, and the idea of handles and the claim, the important fact number 2, formalizes that assumption for us.